All right, so we should do number 15, no, number 57 in 14.7, which says f of x and y is the square root of x plus 2y plus 1. And first it wants me to compute a local linearization at 0, 0. Cool? Okay, what do I need to compute a local linearization anywhere?
Partial derivatives of x and y. The first part of the Taylor approximation, basically.
Yeah, I just need to make the first order Taylor approximation, right? So my linearization as a function of x and y should be, dumbest guess is
f of x and y.
f of x and y evaluated at 0, 0, right? Which should be 1. Okay, that's my 0th order Taylor approximation, right? Like literally dumbest guess you can come up with. Then your next dumbest guess is to what?
Partial
Yeah, make the slopes match, right? Okay, so I need partials, yeah?
Yep.
Okay, so because they're going to ask me for a bunch of partials, I'm going to start computing over here. So, and I should be good about notation. So I need fx of x and y and fy of x and y. And what do you get? Okay. Stay. No. Stop it. Stay.
I had 1/2 √x times x. That was another kind of part of my confusion. I'm still not 100% sure on when you keep the x's and y's and when you don't. Like, if you're taking the partial for x in this case, would you drop the y out or would you leave it because it's all under the radical?
Okay, so I think maybe I need to,
Oh yeah, just because of the.
let me think about this as stuff, specifically x plus 2y plus 1, right? All to the 1/2 power. So I should drop the power down, right? So I'm going to do 1/2, and then I should get the stuff, all of it, because I'm using the chain rule, right?
Yeah.
To the what power?
Negative 1/2.
-1/2. And then here I should have times the derivative of the inside, which in this case is 1, because I'm differentiating with respect to x. Okay, so all told here I get 1/2 square roots of x plus 2y plus 1. And then the fy should be similar, right? The first bit should be the same. I should have 1/2 root x plus 2y plus 1. But what else was in there? I needed a derivative of the inside with respect to y, right? So I really need another 2 there. So I may as well toss the 2 up top, and then I can reduce a little. So I'll get 1 the square root of x plus 2y plus 1. You guys all good with that? Okay, then what?
Throw the slopes down and have x minus, well, it'd just be x because it's 0.
Okay, so I should have some kind of x slope, right? Should be x minus 0 here. So this is an x run, right? And then I should have a y run over here, so that should also be y minus 0.
And you plug 0, 0 into your 2 slopes then?
Oh, good. Why am I plugging 0, 0 into the slopes and not just putting that crap right here?
You want it at that point.
Yeah, because that should be a slope of a tangent line, right? Not the slope of all the tangent lines. So you need to plug 0, 0 in there. What do you get? 1/2 and 1/1. Okay, so all told here I get 1 plus 1/2 x plus y. And that's my linearization in terms of x and y. You guys all good with that?
On local linearization, like the 1 in the beginning, sometimes you put the 1, or like the f of AB, and sometimes you don't. Like you equal it to 0, you don't have the f of AB. Can you explain what that is?
by equal
Like,
to
I don't
zero.
know, in the book when you're
Well,
doing,
there's some of the tangent plane
yeah,
problems in the book. Sometimes they had like a Z coordinate there.
yeah.
And
Oh.
sometimes they would omit that. And there wasn't really a rhyme or reason.
Yeah, so the book's writing their planes in two different ways, right? So a tangent plane might be written as z equals some number plus some number x plus some number y, right? Like that's one way to write a plane down. Another way they might write a plane is they might write 0 equals some number plus some number x plus some number y plus some number z.
Right.
So it's just, have they moved the z over to make the standard form of a plane, or do they have a function of x and y?
But then they also get rid of the f of a, b in the beginning, like the 1, they don't have that. Every time it's equal to 0, they like don't have that first thing. And I couldn't figure out why. I've been trying for a while.
Presumably it's just that f of ab is 0. That's my best guess.
Okay,
Yeah, but that thing should be in there anytime you're actually
Anytime.
computing a tangent plane.
good to know.
Yeah, that thing ought to be in there.
So I might have defined this out, but what's with the zeros again? Why is it
So
zeros?
the zeros are because my local linearize included the at 0, 0.
Okay, just making sure.
So those are where my x and y are based, right? Which is why I'm evaluating everything here at 0, 0. You guys all good on this? Okay. Part B says compute the quadratic Taylor polynomial.
This would be the same thing then, but with the x-axis, the y-y, and xy.
Good, yeah, so I need the next order derivative to add the extra terms to this thing, right? So let me just, maybe I won't. All right, so I'm going to call this q of x and y, right? For quadratic. So that's going to be 1 plus 1/2 x plus y. Why do I get to just write that crap down?
That's all included in the quadratic.
Yeah, that's the first order Taylor polynomial, right? That's like your dumbest guess so far. And then how can I improve my dumbest guess so far?
Add it.
Then fxx, yeah.
So there should be here, let's see, like this should be fxx stuff times what?
Fxy.
The x run squared.
Yeah, I need x run squared there.
Oh, sorry.
So I'll need an x squared there.
You're gonna have a y run squared.
And I'll have a y run squared. It's over there. And in the middle, I need a
Two
X run times the y run.
an x run, y run. Okay, and then what else shouldn't I forget in here that I almost forgot the last time I wrote these down?
Divided by 2.
At point, slope point.
So close.
Divided
What
by
else?
2.
Yeah, I forgot divided by 2's last time, right?
Part of it.
So this is going to be over 2. This is going to be over 1.
1.
Yeah, because it's.
Oh, yeah.
Yeah, because there's 2 of them, right? That should be fxy and fyx, which are generally the same.
So ignore it.
So we should slash that too, but this guy should get an over 2.
Yeah.
Okay, so now I need to compute some derivatives, right? Okay, so I need fxx as a function of x and y, which should be, What do you get? Oh my God, help. Where do I start?
Well, I'm kind of confused because like the first one, you just with the partial of x seems like it'd be the same as this one, right? There wouldn't be any x's left to derive.
Well, that'd be the partial of x with partial.
So I need to, what this says, right, is take the partial with respect to x of f, and then differentiate that with respect to x. So the place you should start is the partial with respect to x that you already did, and then you should hit that with a ddx, right? So I should be doing the partial with respect to x of that thing. So I'm going to say that's 1/2 x plus 2y plus 1 to the minus 1/2 power, right?
And you just do partial for x is like that.
Yep, and I need to do the partial with respect to x at this thing. So I got minus 1 over 4, and then all of this crap, x plus 2y plus 1 to the negative 3 halves, and then times the derivative of the inside, right, which is 1. You guys cool on that? Yeah, kind of?
Wait, so that was the second partial derivative with respect to x?
Yep, so that's fxx, right? That's do the x derivative once, I got to here. Do the x derivative to that. So I got this mess.
And then to write the negative 3/2 power cleanly, that'd be like the square root over 3 on the left-hand side, right?
Okay, so to write that out, that'd be -1 over 4 square root of x plus 2y plus 1, and then cube all the crap that's in the square root. You could cube the stuff inside first and then square root it. It doesn't actually matter. You guys cool with that? Yes? Cool? All right. How about fxy? So which one is this?
This is the x, then it's the x one, then you add, then you,
Yeah, this is the x one, and then you do the y derivative of that, right?
Presumably it doesn't matter.
And presumably it doesn't matter because this is kind of a nice, easy function, right? So Clairose says if the function is easy, then the mixed partials are equal. Yeah. Yeah, if you're an engineer, then the mixed partials are the same. Not quite right. But you should still be careful. If you wanted to check, you could just take both derivatives, right? Okay, so let me take this one. Where's a good spot to start for this?
Might as well start with that.
Yeah, you better start with the partial with respect to x that you already computed, right? And so you'll get basically the same thing we just got. We'll get a -1 over 4 x plus 2y plus 1 to the negative 3/2 power times 2 instead of 1. Guys all good with that?
yep.
Okay, and then I need fyy of x and y, which should be dang near the same thing, right? So I take that guy, and I need to y differentiate. So I do, this is x plus 2y plus 1 to the
Negative 1/2.
negative 1/2 that I'm differentiating with respect to y.
Yep.
So I take the power down, I got negative 1/2, and then what?
X plus 2y plus 1 to the power of negative 3/2.
X plus 2y plus 1 to the negative 3/2 power times
2.
the derivative of the inside is 2, right? Plus. And we could slash it 2 there, but it doesn't really matter. So why doesn't it really matter?
Because 1 to the negative 3/2 is 1.
Yeah, because you're just going to plug 0, 0 into all of these anyway, right? Okay, so when I take fxx and evaluate at 0, 0, I get
Negative 1/4.
negative 1 over 4. So I put that in here, negative 1 over 4. And then I have to remember that over 2 that's on that coefficient, right?
That becomes negative 2 over 4 then? Negative 4 over 2? Oh my god. You're dividing by...
You're dividing by the whole
So you're
number
taking
two.
a quarter, right? So if you have a quarter tank of gas and you want to go 2 ways,
So it'd be negative 1 each
yeah, you need an eighth of that tank to get each way, right?
one. Okay.
Okay, so this should be all told, maybe I should rewrite my Q. So Q of x and y is 1 plus x over 2 plus y minus an eighth x squared. Okay, and then what's fxy evaluated at 0, 0?
Negative 1/2.
This bit's all 1, right?
Yep.
So I got negative 2 over 4 is
Negative 1/2.
negative 1/2 xy, and fyy at 0 is
Negative 1. But then
negative 1, and I need the over 2. So I get a minus 1
over 2
over 2
y squared.
y squared. There's my quadratic approximation.
So this, so the Taylor series can't perfectly hit a square root function because the square root is not actually a polynomial, right?
Yeah. Okay. You guys all see that? So the reason I'm not getting exactness, right, is that I've made a second degree polynomial trying to approximate a non-polynomial function, right? And so at best, this is an approximation. You guys all see that? So this was an approximation with a tangent plane, right? So I had some friggin' handkerchief weirdness going on, right? And then my first degree approximation was to find a tangent plane, right? What does my second degree approximation do? Yeah, it finds a tangent paraboloid. You guys all see that? So when they ask here in this last question, like, compute the values of a linear and quadratic part A and B for some points, which approximation gives the closest values? What's the answer to that going to be in general? Like just ballparking, which of these things is going to be better?
Probably where one's most positive.
Quadratic.
Yeah, why is the quadratic one going to be better?
It's getting closer to the.
Probably, right? You have some bent thing, right? And you're approximating that bent thing with either a tabletop or a
Slightly more.
slightly less bent thing. You guys see that? The bent thing's probably going to do better. Is that true for every function and every set of points? Hell no.
Do we still have like those ranges of accuracy?
Yeah, so there's still ranges of accuracy here. This thing is still going to, in general, be more accurate than that, but it's not always more accurate. You guys want a Calc 1 example for that always but not, or almost always but not actually always more accurate thing? Maybe let me draw a picture and we'll say this. Okay, so here's some generic function, right? Like I'm doing the Calc 1 version of this. Say that I'm talking about right here. If I draw a tangent plane to this, or a tangent line, right? The one-dimensional analogy. My tangent line is going to look like this. You guys see that? So where is this tangent line a good approximation to the function? Like someplace in here, right? But also
For one point.
over there for one friggin' point where it happens to hit. You guys see that?
That's not intentional.
Yeah, exactly. That's not intentional, but it happens. If I draw a parabola in here, right? My parabola is probably going to look something like this.
That's pretty crappy.
Shut up. You guys see that? So maybe I have, like, blue is accurate kind of on some interval like this. Red is probably accurate on a slightly larger interval, but it didn't happen to hit over there. You guys see that?
Okay.
So just by freaking happenstance, the blue one's a better approximation over there than the red one is. Does that mean anything?
No.
Not really, but I want you guys to know that that happens, right?
Wouldn't the likelihood of that quadratic actually come back up once?
If it was a higher
It can't come back up once, it's a quadratic.
Oh, yeah.
22-degree quadratic.
But if we made
I'm
a
thinking-
fourth degree polynomial approximation, right, then it would probably kind of burble. If we made a third degree approximation, it would look like this, right? You guys all kind of with me on those? You remember these a little bit? Okay, so when they ask for you to tell which one gives you the better approximation, probably it's the quadratic. But sometimes you get lucky with a linear one and it just hits somewhere kind of out there. I don't think that happens with this one. My guess is that the quadratic's better in all cases on this one. But it should happen. Cool? Questions, Steele?
Good question.